The biggest cosmic encounter since Oumuamua, and the world's most powerful space agencies have gone completely dark. On October 3, 2025, an interstellar comet named 3IAtlas buzzed Mars, and the only proof we have is a ghostly smudge found by citizen scientists in public data. With billions of dollars of technology pointed right at it, the official images are missing in action. So, are we looking at a cover-up, a colossal failure, or the quiet prelude to a discovery that will change everything? Let's explore this together. The Flyby. You have to understand, this wasn't just another cosmic event, it was a rendezvous that scientists have dreamed about for decades. On October 3, 2025, the interstellar comet 3IAtlas made its closest approach, skimming just under 0.2 astronomical units, that's about 29 million kilometers from the planet Mars. To put that in perspective, that's closer than any planet ever gets to another, outside of a collision. This flyby was a moment of incredible cosmic alignment. For the first time, a visitor from another star system was set to pass directly through a region of space monitored by a dedicated fleet of advanced scientific instruments. Every major space agency with a presence at Mars, from NASA and the European Space Agency to China's CNSA and the UAE's HOPE mission, had a front-row seat. Mission planners, like Dr. Jim Bell, the principal investigator for Perseverance's Mastcam-Z cameras, scrambled to redirect their assets. This wasn't in the original mission plan, but an opportunity like this is too valuable to ignore. The calculations were precise, the stakes were enormous, and the entire planetary science community held its breath, waiting for a flood of data from our robotic eyes at Mars. The promise of Mars. This was never just about getting a cool picture. This alignment was a once-in-a-generation chance to answer some of the biggest questions in planetary science. Having a world-class laboratory already in orbit around Mars meant we could study 3IAtlas in ways impossible from Earth. Think about it. The Mars Reconnaissance Orbiter's HiRISE camera could potentially see the comet's nucleus or any fragments breaking off. Spectrometers like Omega on Mars Express or the NOMAD instrument on the Trace Gas Orbiter were ready to taste the comet's atmosphere. Dr. Nicholas Thomas, who leads the team for the CASIS camera, knows these instruments are sensitive enough to detect the unique chemical fingerprints of interstellar ice. Are the building blocks of life the same in other star systems? Is the water in this comet similar to ours? These instruments were designed to answer exactly those questions by analyzing the gases in the coma. It was a chance to perform a chemical autopsy on a pristine sample from another star system, testing every theory we have about how planets are made. Every asset was pushed to its absolute limit for this cosmic flyby. A faint signal emerges. With the world's space agencies silent, the first and only evidence of the flyby came not from an official press release, but from the hard drives of two persistent citizen scientists. Enter Björn Jónsson and Kevin Gill, two names legendary in the community for their meticulous processing of raw space images. Working independently, they went directly to NASA's Planetary Data System, the public archive where raw data from missions like Perseverance is posted. Within hours of the data being downlinked, they began their digital excavation. Their process was painstaking. They took dozens of long-exposure images from the Mastcam-Z camera, which were designed to look at the dark Martian sky. By aligning each image based on the background stars, and then digitally stacking them, they could amplify the faint signal of anything that moved through the frame. After methodically subtracting sensor noise and cosmic ray hits, a faint, diffuse patch of light emerged, right where 3IAtlas was predicted to be. It wasn't a spectacular photo, but it was monumental, the first and only direct confirmation that the interstellar visitor had made its historic pass. Their work stands as a testament to the power of open data. The auditable path. Seeing a faint smudge in an image is one thing, but proving it's actually an interstellar comet and not just, random noise is another challenge entirely. The path to this detection had to be auditable, meaning every single step was carefully documented and reproducible. The analysts started with raw, 29-second exposures from Perseverance's Mastcam-Z camera. The principal investigator for this camera, Dr. Jim Bell, designed it for incredible scientific precision. For each image, the team had to find a matching dark frame, which is basically an image taken with the lens cap on, to map out and subtract the camera sensor's inherent electronic noise. Then came flat field corrections to account for dust on the lens, and variations in pixel sensitivity. Next, they had to align, or register, each image with sub-pixel accuracy against a star catalog. Only then could they stack the dozens of clean frames. They used multiple methods to combine the images, which boosts the signal of a faint object while averaging out random noise. The final step was to model and subtract the Martian sky's background glow. What was left was the detection. A signal statistically strong enough to be real. This wasn't guesswork, it was a forensic process. Viral myths and reality checks. In the vacuum of official information, the internet did what it does best. It generated myths. The moment the faint real detection began to circulate, so did much more dramatic but fake images. The most viral was a sharp, razor-thin streak of light in a single frame from Perseverance's navigation camera. It was hailed as a naked-eye view of the interstellar comet, but the truth required a dose of orbital mechanics. Dr. Emily Lakdawala, a renowned planetary scientist and author, did what any good scientist does. She checked the numbers. Using JPL's Horizons Ephemeris tool, which can predict the position of any known object in the solar system, she plotted the streak's path and timing. The verdict was undeniable. The streak perfectly matched the speed, orientation, and sky path of Phobos, Mars's inner moon, during a long exposure. The second myth was a bright, fast-moving streak in a different Mastcam Z frame. Again, the math didn't add up. Its angular velocity was at least 10 times faster than 3IAtlas was predicted to be moving. It was likely a meteor in Mars's upper atmosphere, or a simple sensor artifact. These episodes were a critical lesson in scientific literacy. Not every streak in the sky is a visitor from another star. The silent orbiters. So, where were the multi-billion-dollar orbital missions while citizen scientists were making the only public detection? The silence is what makes this story so strange. Let's be clear about what we are missing. The Mars Reconnaissance Orbiter carries the HiRISE camera, a telescopic instrument so powerful it can spot a coffee table on the Martian surface from 300 kilometers up. Its principal investigator, Dr. Alfred McEwen, and his team could have delivered the sharpest image of an interstellar object ever seen. The ESA's orbiters were ready to perform a chemical analysis. The trace gas orbiter can detect atmospheric gases in trace amounts. If 3IAtlas was venting anything unusual, any molecule not seen in our own comets, it would have found it. The UAE's HOPE and China's Tianwen-1 were also observing, providing a global network of coverage. The potential for a breakthrough was immense. Yet, as of today, not a single raw image, spectrum, or even a low-resolution thumbnail has been released to the public. The data is either under embargo, stuck in a processing queue, or, well, something else is going on. The knife's edge. The silence from the space agencies probably isn't a conspiracy. It's a reflection of the brutal reality of deep space operations. Pointing a spacecraft at a tiny, fast-moving object millions of kilometers away is, honestly, an exercise in controlled terror. The ephemeris for 3IAtlas, its predicted position, was being updated hourly. But the orbiters can't just react in real time. The commands to turn, point, and shoot have to be programmed and sent hours or even days in advance. It's what engineers call open-loop pointing. You shoot and just hope the target crosses your field of view when you scheduled it to. Then there's the Deep Space Network, the communication lifeline to Earth. Every bit of data from every mission at Mars competes for limited bandwidth. A historic image from HiRISE might, have to wait in a queue on the orbiter's solid-state drive for days behind higher-priority engineering telemetry. A single missed DSN window or a slight drift in the comet's predicted path could mean the difference between a Nobel Prize-winning image and a frame filled with empty black space. This is the knife's edge of interplanetary observation. Blinded by the sun. Just as the mystery of the missing data deepened, the curtain came down on any new observations from Earth. And, this isn't a conspiracy, it is just orbital mechanics at work. As October advances, 3IAtlas is approaching what is called superior conjunction, which means it passes almost directly behind the sun from our perspective. This celestial alignment, happening around October 21st and 22nd, effectively blinds us. The sun's overwhelming glare makes it impossible for any ground-based or near-Earth telescope to safely observe the comet. The comet's most active phase, its closest approach to the Sun, what astronomers call perihelion, happens on October 29th, right in the middle of this blackout. As Dr. Michael S.P. Kelly has noted in his research, this is the most critical time to observe a comet for outbursts. It's when the comet should be at its most dynamic, and yet, we are completely unable to watch. This blackout will last until early December. So for now, the silence from the Mars orbiters is compounded by a physical barrier. The universe itself has blocked our view, leaving us to wonder what is happening in the glare. The working hypothesis. Based on the limited data gathered before 3IAtlas disappeared into the Sun's glare, scientists have a working hypothesis, but honestly, it's full of questions. The current theory is that 3IAtlas is a natural interstellar comet, but one with a very strange chemistry. Early spectra suggested it's rich in carbon dioxide ice, but surprisingly poor in dicarbon, the molecule that gives most of our solar system's comets their classic green coma. This points to an origin in a star system with a very different chemical makeup or temperature gradient than our own. Some of the provisional reports also hinted at a possible excess of metals like nickel in its dust, a finding that, if confirmed, would be truly bizarre and pretty hard to explain. Dr. Stephanie Malam, an expert in comet chemistry at NASA, would be chomping at the bit for the orbiter data, since only high-resolution spectra can confirm these tantalizing hints. Without that data, the natural comet scenario remains just that, a hypothesis. The real proof is still sitting on a hard drive, waiting to be processed. What remains and what comes next? The data from the Mars flyby might be out of reach for now, but the story is not over. There are a few long-shot possibilities for observation during the solar conjunction blackout. The SOHO spacecraft, which constantly stares at the Sun, has a coronagraph called LASCO C3 that might catch a glimpse of the comet. It's not very sensitive, so it would only see 3IAtlas if the comet had a major outburst and brightened dramatically. Farther out in the solar system, the European Space Agency's JUICE spacecraft is on its way to Jupiter. Experts like Dr. Geraint Jones have confirmed that there might be a brief window in early November where JUICE could try to image the comet. But honestly, the real action will begin in late November or early December. That's when Earth's motion carries us out of the solar glare, and ground-based telescopes can finally get back in the game. When that happens, expect every major observatory to be pointed at the patch of sky, trying to recover the faint receding visitor. Until then, the only confirmed public detection remains that single faint stack of images from Perseverance. The story of 3IAtlas is a cliffhanger. We have a confirmed detection, a mountain of unanswered questions, and the most important data in a generation locked away, waiting for processing. This event has exposed both the incredible power of our robotic explorers and the frustrating limitations of deep space science. Was this just a strange comet, or is it something more? The answer is coming, but for now, we wait. This is a powerful reminder that the universe still holds deep mysteries, right on our cosmic doorstep. Don't forget to like, subscribe, and hit the bell icon for more explorations into the cosmos. Thanks for watching Stellar Tech.